There's a machine in Chile that was never built to take pictures of the sky. It was built to watch the sky change. It stares at the same stretch of sky over and over every few nights for 10 years, and the instant anything moves, brightens, explodes, or appears out of nowhere, it flags it. Millions of times every night. But here's the strange thing about a machine like that. It doesn't just find what we pointed at. It finds things we didn't know to look for. And I can prove that to you, because it already has. Before its real mission had even started, while it was still being tested, this telescope photographed a visitor from another solar system, an object from around another star, just passing through ours. It caught it 10 full days before the astronomers who officially discovered it even knew the thing was there. And that might be the most important thing about the Vera Rubin Observatory. It isn't just better at finding what we're looking for. It is built to catch what we don't even know to search for. So, if a visitor from another star could sit in this telescope's images for 10 days before a single person noticed, what else have we already looked straight at and missed? Before this telescope switched on, 3 was the entire count of objects humanity had ever confirmed from beyond our own solar system, in all of recorded history. On July 1st, 2025, a network of telescopes flagged a comet moving through our solar system. That part isn't rare. You hear about new comets all the time. But this one was moving wrong. It was coming in too fast and on the wrong kind of path. Not a loop around the sun like every comet born here, but a straight shot through, on a trajectory the sun's gravity could never have bent into place. It was moving at roughly 130,000 miles an hour relative to the sun, far too fast for our star to ever catch it and hold on. And that can only mean one thing. It didn't come from here. It was a piece of another solar system, thrown out into the dark millions of years ago, just drifting through ours on its way back out. We named it 3I Atlas. And in all of recorded history, it was only the 3rd object like it we had ever confirmed, after Oumuamua in 2017 and Comet Borisov in 2019. Now, here's where the Rubin Observatory walks into the story. After 3I Atlas was announced, astronomers did something simple. They went back and checked whether any other telescope had happened to catch it earlier. And there it was, sitting quietly in Rubin's very first test images, taken on June 21st, 2025. 10 days before the official discovery, this telescope had already photographed the visitor and moved on, without a single person realizing what it had captured. Had those images been recognized first, the object might have ended up being called 3I/Rubin. Everyone assumed that spotting a visitor from another star was a once-in-a-decade stroke of pure luck. Rubin caught one in its first week, by accident, before its mission had even begun. It wasn't looking for it, and it found it anyway. And that's the whole point. Because if that's what it does while it's still warming up, the real question isn't what it will find on purpose. It's how much is slipping past us right now that nobody has ever thought to look at. Now, we come to the telescope itself. The heart of it is a camera the size of a small car. To understand what it's really built for, start with where it lives. It sits nearly 9,000 feet up in the Chilean Andes, above most clouds and city glow. Its mirror is nearly 28 feet across, about as wide as a tennis court, and bolted to it is the largest digital camera human beings have ever built. It captures 3,200 megapixels, enough to fill 400 4K televisions with a single image. And it never lingers. A fresh image every 40 seconds, all night, every night. The reason it carries the name it does is the part I find genuinely moving. It's named after an astronomer named Vera Rubin. Decades ago, she was measuring how galaxies spin, and she found something that shouldn't have been possible. She measured how fast stars orbit at different distances from the centers of galaxies. You'd expect the outer stars to move slower, just like the outer planets in our solar system. But they didn't. The outer stars were sweeping around just as fast as the inner ones, on a flat line that made no sense. Unless there was several times more mass out there than anything anyone could actually see. Something invisible was holding those galaxies together. Her work became some of our strongest evidence for dark matter. Mass we can't see, only its gravity. Here is what her namesake telescope was built to do about it. We still can't see dark matter, but its gravity bends the light of distant galaxies. Measure those tiny distortions billions of times, and the invisible takes shape. A map of the dark scaffolding of the universe. And the same measurement reaches at something stranger still. The expansion of the universe is speeding up, driven by something we call dark energy. And we don't know what it is, or even whether it holds steady over time. And recent results from other surveys suggest it might not. Vera Rubin spent years measuring something nobody could see, only the way it pulled on everything around it. She died in 2016, almost a decade before the machine that carries her name ever opened its eye on the sky. Rubin was built to put that question to one of its most powerful tests yet. And so the woman who first found the fingerprints of the invisible universe now has a machine carrying her name, built to trace its outline across billions of galaxies. The most unsettling thing this galaxy hunting telescope has done so far, it did right here in our own backyard. In just a few weeks of early testing, before the real survey had even begun, Rubin found more than 11,000 brand new asteroids that no one had ever recorded. 11,000 in about 6 weeks. Among them were 33 new near-Earth objects. But cataloging the asteroids we can already see was never really the point. Rubin's job is finding the faint, dark, overlooked ones we can't. The small bodies that have been slipping silently past every other telescope for decades. Which means the unsettling number was never how many it found. It's how many are still out there, unlit and uncounted, that we simply never had the eyes to see. And Rubin doesn't just count these things, it clocks them. In that same early data, it caught the fastest spinning large asteroid ever found, a rock nearly half a mile wide, turning so fast it completes a full rotation every 1.9 minutes. It became the first peer-reviewed discovery ever published from Rubin's camera. And remember, this was 6 weeks of warm-up. And it reached further out, too. In that same early data, it turned up 380 new worlds beyond Neptune, icy bodies drifting in the cold, dark edge of the solar system. A couple of them ride orbits so stretched that they swing nearly 1,000 times farther from the Sun than we are. And orbits like those matter, because for years astronomers have suspected something enormous is hiding out there. A possible 9th planet, maybe 5 to 10 times the mass of Earth, quietly tugging on the paths of these distant objects. Nobody has ever seen it. We only suspect it's there because of what it does to everything around it, the same way Vera Rubin first sensed dark matter, by its pull rather than its light. If Planet 9 is real, Rubin may have one of our best chances yet of actually seeing it. But over 10 years, by catching enough distant objects with strangely bent orbits, it could finally reveal whether something really is out there bending them, or whether it never was. A star sits in tonight's image, exactly where it sat 3 nights ago. Look again 3 nights from now, and it's gone, or blazing thousands of times brighter, because in between, it exploded. Because this is where watching the sky, instead of just photographing it, becomes something you can actually feel. That's a supernova. A dying star briefly blazing brighter than its entire galaxy. But they don't last. They flare, then fade. So for most of human history, if nobody happened to be looking at the right patch of sky, we simply missed them. Rubin never looks away. It returns to the same sky every few nights, lays tonight's image over the last one, and any star that brightened, dimmed, moved, or vanished lights up as an alert. String enough of those nights together, and you stop looking at photographs and start watching a movie. Picture a flipbook, except every page is the whole southern sky, and it runs for 10 years. You don't get a snapshot of the universe, you get footage of it. But here's what turns it from a camera into something more. The instant it flags one of these, it can tell the rest of the world within minutes, while the explosion is still unfolding, and telescopes across the planet swing around to catch it before it fades. Rubin isn't just the observer anymore. It's the alarm that makes every other telescope move. A wide image can tell you that something changed. It cannot always tell you what. Most of what Rubin flags will be supernovae and flaring galaxies we already recognize, but scientists fully expect that somewhere in that stream will be explosions of a kind we have never seen, that match nothing in the textbooks, events we don't yet have a name for. And that's the next rung of the same ladder. Not an object we missed, not a planet we can't see, but a whole category of thing that might not exist in our science yet, waiting in a river of light no one has finished reading. 10 million. That's how many alerts this telescope can fire in a single night. 10 million flags, each one saying that something in the sky just changed, riding on about 10 terabytes of fresh data. Over the full survey, Rubin's data processing could generate on the order of 500 petabytes of data. To put that in plain terms, that's roughly the equivalent of every word human beings have ever written in every language across all of history from a single telescope. And this isn't a someday promise. On one night in February 2026, Rubin switched its alert system on for real and fired off 800,000 of them before sunrise. 800,000 changes in the sky flagged in a single night on the very first full run. That's what it does today. The 10 million is just where it's headed. Most will be things we already know: variable stars, asteroids, supernovae, active galaxies. But no team of humans could ever inspect 10 million events a night. And that runs straight into something uncomfortable about how discovery has always worked. So many great discoveries began with someone noticing something that didn't belong. But no human eye will ever scan this river. So the noticing itself has to be handed to machines. AI brokers sift the flood, rank what's strange, and pass only a tiny fraction to humans. And that's the paradox sitting at the heart of the most powerful eye ever built. We've finally made a machine that can find things we don't yet know exist. But it sees so much that a second machine has to decide, millions of times a night, what even counts as interesting. The serendipity that drove 4 centuries of discovery, the lucky glance, the human hunch, now has to be taught to an algorithm. Which brings us all the way back to where we started. For 400 years, we pointed telescopes at the things we wanted to see, and we took their picture. Now, for the first time, we have a machine that simply watches the whole southern sky every few nights for a decade, catching everything that moves, brightens, or appears out of nothing. It was built for specific answers: dark matter, dark energy, asteroids, the far edge of the solar system. But think about what it means to open an eye this wide, this deep, and this fast for the very first time. The most important thing it finds may not be anything it was sent to look for. It may be something we don't even have a name for yet, because no one has ever seen it. And here's the thought I can't shake. Rubin already caught a visitor from another star, sitting in its images for 10 days before anyone knew to look. Every night now, it flags millions of changes. And somewhere in that flood, among the millions of things no human will ever inspect one by one, there may already be something extraordinary. A signal we would recognize as historic, if only someone were looking. The sky isn't a picture anymore. It's a river. And we just built the first machine fast enough to watch it flow, and quiet enough to wonder what we're letting drift past.